Welcome to the lesson on properties of a triangle. At the end of this lesson, you will be able to prove that angles opposite to equal sides of an isosceles triangle are equal, and that sides opposite to equal angles of a triangle are equal. You will also be able to solve problems based on the properties of an isosceles triangle. Consider this triangle. Can you determine its type? On measuring its sides, we can see that two of its sides are equal. It's an isosceles triangle. The third side becomes the base of the isosceles triangle. Now, let's join the vertex to the base of the triangle. If we fold the triangle along this line, it divides the triangle into two equal right-angled triangles. As you can see, the corresponding sides and angles of these two triangles are equal. Coming back to the isosceles triangle, we have two equal sides, and the angles opposite to these sides are also equal. Based on these observations, we can conclude that angles opposite to the equal sides of an isosceles triangle are equal. We will prove it by using the criteria of congruence. Consider two triangles. For these triangles to be congruent, the sides and the angles of one triangle must be equal to the corresponding sides and angles of the other. Congruency of triangles can be proved using the four criteria of congruence: SAS congruence rule, ASA or AAS or SAA congruence rule, SSS congruence rule, and RHS congruence rule. Using some of these criteria, we will prove two important theorems of an isosceles triangle. To prove that angles opposite to equal sides of an isosceles triangle are equal, we'll consider an isosceles triangle ABC. Here, side AB is equal to side AC. We have to prove that angle B is equal to angle C. Angle B is opposite to side AC, and angle C is opposite to side AB. We'll begin by drawing a bisector of angle BAC meeting BC at D. First, we will show that triangle ABD is congruent to triangle ACD. In triangle ABD and triangle ACD, side AB is equal to side AC. This is because triangle ABC is isosceles. Angle BAD is equal to angle CAD, since AD is a bisector of angle A. Side AD is common to both the triangles. Now, by Sas axiom, if two sides and the included angle of one triangle are equal to the two sides and the included angle of the other triangle, then the triangles are congruent. Thus, triangle ABD is congruent to triangle ACD. And since the corresponding parts of the congruent triangles are equal, therefore, angle B is equal to angle C. This was simple, wasn't it? The converse of the above theorem is also true. Let's try proving it. The sides opposite to equal angles of a triangle are equal. Let ABC be the given triangle. in which angle B is equal to angle C. Using this information, we'll prove that side AB is equal to side AC, which are the sides opposite to the equal angles. Like we did in the previous proof, here too, we'll draw a bisector from the vertex to the base. This divides the triangle into two triangles. After that, using the criteria of congruence, we'll prove that the resulting two triangles are congruent. Then using CPCT, which implies that corresponding sides are equal, we'll prove the converse theorem. Let's draw bisector AD of angle BAC meeting BC at D. Thus, two triangles ABD and ACD are obtained. In triangle ABD and triangle ACD, we are given that angle B is equal to angle C. Angle BAD is equal to angle CAD, since AD is bisector of angle A, and side AD is common to both the triangles. Now, as we know, by the AAS criterion, if two angles and one side of one triangle equals two angles and one side of the other triangle, then the two triangles are congruent. Thus, triangle ABD is congruent to triangle ACD. And since corresponding parts of congruent triangles are equal, side AB is equal to side AC.